Let us consider a binary liquid mixture of a solvent A and a solute B at equilibrium with a mixed vapor phase containing A and B species. As was discussed on the preceding slide, the Gibbs energy of the mixture is equal to Na mu A liquid plus Nb mu B liquid. Assume that we transfer reversibly a small amount of A, which we call DNA, from the liquid phase to the vapor phase. This process is associated with a change in Gibbs energy of the system expressed as dG equals dNA times mu A for the vapor minus dNA times mu A for the liquid, since the vapor phase has gained dNA moles of A, each with chemical potential mu A vapor, while the liquid has lost dNA moles of A, each with chemical potential mu A liquid. We can factor out the term dNA and obtain dG equals dNA times mu A vapor minus mu A liquid. Since the transfer from the liquid phase to the vapor phase occurs reversibly, this implies that dG is equal to 0, or we have a local equilibrium. Hence, we conclude that mu A for the vapor phase minus mu A for the liquid phase is equal to 0, or mu A vapor equals mu A liquid. We can follow the same approach for the reversible transfer of dNb moles of B from the liquid phase to the vapor phase and conclude that mu B vapor must be equal to mu B liquid. This line of reasoning can be extended to all phase equilibria in multi-component systems and allow us to state that when a multi-component, multi-phase system is at equilibrium, each substance has the same chemical potential in all the phases. Our goal is to obtain an expression for the change in Gibbs energy for the solution as a result of mixing. To calculate such a quantity requires that we know the chemical potentials of solvent and solute in solution. While we do not have simple or accurate expressions for these chemical potentials in solution, we can use the result obtained on the preceding slide, where we learned that for a multi-component liquid-vapor equilibrium, the chemical potential of A is the same in the liquid phase as in the vapor phase, and the chemical potential of B is also the same in the liquid and vapor phases. At the beginning of Chapter 3, we already discussed how the Gibbs energy changes with pressure for ideal gases. Since ideal gases do not exhibit intermolecular interactions, their Gibbs energy will be the same regardless of whether they are pure or mixed with other gases. Let us review briefly this calculation using the new notation of chemical potential, equivalent to Gibbs energy per mole. We started with the expression of the change in molar Gibbs energy, dGm, associated with a small change in pressure, dP, and a small change in temperature, dT, and wrote dGm equals Vm dP minus Sm dt. Let us then say that we are examining a solution at constant temperature, so dt is equal to 0 and dGm is simply Vm dP. If the system is an ideal gas, the molar volume Vm changes with pressure, and integration of dGm requires that we replace Vm by RT over P, so we eliminate an unnecessary variable. Integration of dP over P from P standard to P leads to Gm at T and P minus Gm at T and P standard equal to RT times the natural logarithm of P over P standard. We rearrange this equation as Gm at T and P equal to Gm at T and P standard plus RT times the natural logarithm of P over P standard. We can now replace molar-Gibbs energy with chemical potential mu and obtain mu at T and P equals mu standard at T and P standard plus RT times the natural logarithm of P over P standard. We apply this equation to the solvent A and the solute B in the vapor phase and obtain mu of A in the vapor phase at T and the partial pressure PA equal to mu A standard of A in the vapor phase at T and P standard plus RT times the natural logarithm of PA over P standard. Similarly for B, we get mu of B in the vapor phase at T and the partial pressure P sub B is equal to mu standard of B in the vapor phase at T and P standard plus RT times the natural logarithm of PB over P standard. The variation of mu for component J in the vapor phase at temperature T and partial pressure P sub J minus mu standard in the vapor phase at T and P standard for that same component J divided by RT as a function of the ratio Pj over P standard is shown on the graph plotted on the right hand side. Note that when Pj over P standard equals 1, that is when Pj equals P standard, then mu j minus mu j standard is equal to 0. That is, the chemical potential of species J is equal to the standard chemical potential, as expected. The standard chemical potential is never known. It is only a reference point from which other chemical potentials can be calculated. We will never actually need to know what the value of this reference chemical potential, since we are only interested in changes in chemical potentials or changes in Gibbs energy and are never interested in the actual values of these quantities, G or mu. Using the equations derived on the preceding slide, we can now have a more informed discussion about chemical potentials for solvent and solute in solution. First, we consider the equilibrium between the pure solvent A and its vapor at temperature T, where the vapor pressure of pure A is denoted by PA star. Since vapor and liquid A have the same chemical potential, we write mu A star for the liquid equal to mu A star for the vapor. Second, we use the relationship from the preceding slide to relate the chemical potential for the vapor at pressure PA star to the chemical potential for the vapor at standard pressure. So mu A star for the vapor is equal to mu A standard for the vapor plus RT times the natural logarithm of PA star over P standard. The symbol star will be used in this chapter whenever we are referring to a pure substance. To make a connection with what we learned earlier in chapter 3, you should also note that PA star is obtained from the Clausius-Clapeyron equation for the liquid-vapor coexistence curve at temperature T. So we conclude that mu A star for the liquid phase is equal to mu A standard for the vapor plus RT times the natural logarithm of PA star over P standard. We now consider the equilibrium between the solvent A in the AB solution and the vapor of solvent A in the AB gas mixture above the solution, and follow the same approach as outlined for pure A. We denote the partial vapor pressure of solvent A as PA. We write mu A for the liquid phase equals mu A for the gas phase, and mu A for the gas phase at pressure PA equal to mu A standard at pressure P standard plus RT times the natural logarithm of PA over P standard. This leads to mu A for the liquid equals mu A standard for the vapor plus RT natural logarithm of PA over P standard. We are now in a position to compare the chemical potentials of A in solution to the chemical potential of A in the pure liquid state. Using the above expression for mu A and mu A star for the liquid, we express mu A liquid minus mu A star liquid as mu A standard for the vapor plus RT log of PA over P standard minus mu A standard for the vapor plus RT times natural logarithm of PA star over P standard. This expression can be rewritten as mu A for the liquid minus mu A star for the liquid equal to RT times the natural logarithm of PA over PA star. This is so because the terms mu A standard for the vapor in both terms above cancels out. Similarly, the term RT log 1 over P standard in both terms also cancels out. As mu A for the liquid minus mu A star for the liquid equal to RT times the natural logarithm of PA over PA star. Or the chemical potential of A in the mixed liquid state is equal to the chemical potential of pure A in the liquid state plus RT times the natural logarithm of PA over PA star. Similarly, for the solute B, we write the chemical potential of B in the mixed liquid state equal to the chemical potential of pure B, mu B star, plus RT times the natural logarithm of PB over PB star. These two equations are very general and can be used for any solvent and for any solute at any temperature.